So now that we've seen how heaps work and what their structure is, let's talk about some methods that actually operate on heaps. The first method we're going to take a look at is addElement. So here's the code for addElement, and let's step through this. So anytime we add an element, the first thing we're going to do is we're going to create a new heap node with that element as the element of the node. And so you can see down here we have a new heap node that has left, right, and parent references, and then we have 7 as the element. Now, if the root is null, then we just point the root to the node that we just created. However, if we have a case where the root isn't null, that means that there are existing elements in the heap, then the first thing we're going to do is we're going to call this special method getNextParentAdd, and that's going to tell us what's the parent of the new node that we're adding. So you notice we have references to last node and the root, but we don't have a reference to where's the parent that you're going to add this new node under. So here's some example heaps, and we'll walk through and talk about which node getNextParentAdd should return for each of these. So for this first one, we have a full tree, and so to keep the tree complete, we'll need to add the new node as the first leaf on the new level. And so 12 would be the parent of that new node, and so that would be the node returned. In this heap, again, we want to make sure that it's a complete tree, so we need to add the new node as far to the left as possible, meaning we would add it right here. So 6 is the next parent that we're going to add to. In this case, this would be the next available slot, and again, 6 would be the next parent. Now this case is a little more complicated because this subtree is now full, and so we need to add the new node as the left child of this node, and so that would be the node that would need to be returned. So going back to the heap we saw before, 6 would be the parent of the new node, and so that would be returned by this method, and we'll see how that works in a moment. But for now, let's assume that it's magic. It always returns the right one. So once we have that node, we need to determine, is our new node going to be the left or right child? So if the next parent doesn't have a left child, then that's where the new node has to be added, because we add to the left before the right. And so we'll do that here. And then we set the parent of the new node to next parent, giving us this link. And now that element has become part of the heap. And since that's now the last node we added, we need to update that reference. So then finally, remember we need to keep track of the ordering. And in this case, the order is okay. But to double check that, we'll call this method Heapify Add, which we'll see later. The goal of Heapify Add is to handle cases where, suppose we had a 4 here, then we would need to move the 6 down, move the 5 down, and the 4 would go right here. So that's what Heapify does, and we'll see how that works in a moment as well. So the getNextParentAdd method can be really complicated if you just try to look at the code and understand how it works. And so I always recommend that you get a pen and paper out and trace out what's going on, because that definitely helps you see how that method works. So the first thing we're going to do with getNextParentAdd is we're going to get the last node. And in that case, that's 12. And we're going to set our result to that node. Now this isn't going to be the final result. We're going to use this though as our starting point to find the new parent. Our first loop is going to iterate while the result is not pointing at the root, and also while the parent's left reference is not referring to the result. Now here, this isn't the root. However, the result is a left child of its parent, and so we're not going to iterate into this loop at all for this example. Then, if the result is not the root, which it's not, the first thing we're going to do is check to see, does the parent have a right child? And in this case, it doesn't, so we're going to set the result equal to that parent, and we'll see an example that uses the else case later. And now, we have 2 else cases that we've already dealt with, so we don't need to handle those now, and we're going to return the result. And you can see this will be the next parent because you'll add to the right child here. So what about a case like this where we have a full tree? We would need to create a new level, so this will be the parent, and we'll add the new node as a left child here. So this is the node we want to return. So again, though, we always start at the last node and set our result to that last node. Then here, the result is not the root. However, in this case, this is not the left child. The result is the right child of its parent. So we're going to go to its parent. Here again, we're not at the root, and also the node that result is pointing to is not the left child of its parent. So again, we're going to go to the parent. And now we've reached the root, and so this loop will exit. So here, we first check to see, is the result equal to the root? And here it is, so we're going to go to the else case. What that tells us is that the original tree was full, because the only way you would get all the way to the root is if the result was the right child. So we're basically going up this right side of the tree. Again, we need to get to this node. And so what we're going to do is we're going to go to the left while the result has a left child. So the root has a left child, 5 has a left child, and 12 doesn't have a left child. So we're going to exit the loop, we'll exit the if structure, and 12 will be the result that we return. So here's another case where we've added some more nodes, and you'll notice here that 11 is going to be the parent because we'll add the next node as the left child of 11. Well, the last node is 12, so we're going to set the result to 12. Then, in this case, the result isn't the root, but the left child of the parent of result is not result. So that means result is the right child of its parent. So we move up to the parent. Again, 6 is not the left child, so we go to its parent. And now, result is the left child of its parent. So this loop is now going to exit. Now, the result is not the root. We're going to enter the if condition. And now we need to get to the right subtree there. So results parents get right is not null, it's 3. So we're going to go to the else condition. And now we're going to move result all the way over to the left child. So we were pointing here, now we're going to move to the right child. Then we're going to do the same thing we did earlier. We're going to move all the way to the left until we find a node that doesn't have a left child, and we need to just go down one level to 11. 11 doesn't have a left child, so that case fails, so we exit the loop, and now we return the result, which is 11. So again, I strongly recommend, if you want to understand this code more thoroughly, that you come up with some heaps, make sure they're valid heaps, and trace through them like we did here so that you understand how this works. And again, ultimately the goal is to go from last node to the new parent, to the new node's parent node. getNextParentAdd is what helps us maintain the structural constraint of the heap, which is that it has to be a complete tree. Heapify Add is what we call at the end of our add method to make sure that the ordering constraint is correct. So let's see how Heapify Add works. So let's say we've added a new node, 20 here at the bottom. So we set next to be that last node, and then we store the element there in a temporary variable. So we're checking to see, is the next not the root? And we'll see where that comes into play in a moment. And the next thing we check, is the ordering correct? Is the element we added, which again is temp, is it less than the parent of next? In which case the ordering is wrong. But here we see that it's not less than its parent. So we exit the loop, and then wherever we've determined next is, we set temp to that. And you may wonder, why don't we just do a swap? And the reason it's going to be easier in cases where we have to do multiple swaps. It's easier just to set temp aside and move the values down. And we'll see an example of that in a moment. We move the temporary value back into the node that next is pointing to. That just ensures that we've saved that element. Again, here it doesn't have any effect, but it will in some cases. So now let's say we add a 1. We're going to store the element that we added, which is 1, in our temp variable, and we're going to set temp to the last node. And now you can see that we have some ordering, so we're going to have to do some work. Here we can see that the temp value, which is the value we added, is less than the element stored at the parent of next. So we're going to set the element of next equal to the parent's element. So you can see now we have a 6 in this node. What happened to the 1? Well, we overrode it here, but remember we still have that value here. That's why we're doing the comparison with temp. Then we're going to set next equal to its parent. And here again, the parent of next node has an element that's larger than temp. So we're going to need to set next element to its parent's element. And you can see now we have a 5 there, and we set next to its parent. So now next is pointing here. And again, we're not at the root, but you can see that temp is less than the element stored at next's parent because 1 is less than 2. So we're going to need to bring 2 down. We're going to set next's element to be the element of its parent, which is 2. And then we set next to be its parent, and so it's pointing to the root. Well, when that happens, now this comparison fails. So we exit the loop, and we're going to set the element where next is pointing to our temp value, which is the value we added. And so now our heap is done. So that's a quick introduction to addElement and how its helper methods work. Going back to the original addElement method, hopefully it makes a little more sense now what's going on. We create a new node. We find where we put that node structurally in the heap using getNextParentAdd, and then setting our new node to be the left or right child, depending. Then we call heapifyAdd to fix the ordering structure.